Hello and welcome. My name is Noah Deer. Today we are doing Lesson 11, Directional Derivatives in the Gradient Vector in our Math 254 sequence, Vector Calculus, PCC. Today we're covering directional derivatives. So if we have a function f of, f of x comma y equals z, then we want to look at the rate of change of z as we move in any direction that we please. So instead of just the x direction or the y direction. Then we have the gradient vector, which is actually a vector valued function. It is going to give us its x component is actually the rate of change of x, or the rate of change of z in the x direction. The y component of the gradient vector is outputting the rate of change of z in the y direction. We'll look at that and how it applies to directional derivatives. Functions in three variables, so we'll talk about directional derivatives in the gradient vector for functions in three variables as well. And then we will look at how to find the direction that we have maximum increase of z. So we want to say what is the maximal directional derivative. And it's actually really nice and a simple formula for finding that. Tangent planes to level surfaces, we're going to note that if we have a function in three variables, then if you set the output to a single constant, then we essentially just have a three-variable function. But as we think about it as a three-variable input and a w value output, then we can talk about the directional derivatives here and find that the maximum direction is going to be a normal vector to a tangent plane for that surface. So we'll get there and hash that out towards the end of this lesson. All right, let's jump in here. In this lesson, we consider a surface defined by a function in two variables, z equals f of x comma y, and want to explore the rate of change of z as we move in a direction other than the x direction or y direction. We want to know how to find this rate of change, this directional derivative, and how to determine the direction of maximum rate of change. In this investigation, we will come across what is called the gradient vector, which is actually a vector function in two variables. We will define this formally and come to understand its significance. So like I was saying in the introduction there, that if we have some surface, say this is the curve in the x direction, this is a curve in the y direction on the surface. What if we want to go and find, like at this point, what's the rate of change of z in this direction instead of in the x direction or y direction? So let's take a look. Suppose we have a function z equals f of x comma y, and we want to find the slope of the surface in the direction of u, the vector u equals a comma b, and u, we're making a unit vector, so its magnitude is 1, and it need not be pointing in the x or y directions. Let's take a look at this graph here. This is really going to kind of help us understand what's being talked about. All right, so we have a surface, my blue little spherical-like shape here, and we've got a point P, and we have a unit vector, is this green vector here, and it's pointing in this non-x or y direction, is pointing off to the side here, and then we see, this vector v, this is pointing in a tangent to the surface. It's a tangent vector to the surface in the direction of u. And there's all sorts of parts going on here. I've got this built up for even more conversation moving forward. But we're looking at this specific point P. This is the equation of the tangent line in the direction of u. So this orange line is the tangent line to the surface in the direction of u. And HU is what we're going to do. We're going to start scaling u down. So I'm going to let h go to 0. We see if h is a scalar times u, then we get it being HA comma HB, and we see from the top view here, so u is pointing in this direction, and then we have a delta x is going to be HA and delta y is HB as we move in this direction. So we want to let this go to 0, so delta x and delta y go to 0, so that we're able to find a instantaneous delta z. Let's go ahead and go back to our PDF file. So we're going to define the notation d sub vector u of f of x naught y naught to be the directional derivative of f in the direction of the vector u. That is, this is the rate of change of z as we move in the vector u direction. To come up with a formula for d sub vector u of f of x naught y naught, we note that if we use h as a scalar for the vector u, then as h goes to 0, our direction vector shrinks to a length of 0. So as we do that, then let's look back at the picture again real quick. If we look at this, this is my change in z, right, in the u direction. So this is a change in z if we're moving an entire length of 1 in the u direction. And so then we have our tangent vector down here, so we get this entire change in z. But if we let u go to 0, then the change in z goes to 0. So we really get this idea of change in z over the change in u. So this becomes my derivative as this goes to, I don't want to use it, I don't want to make up a notation. This goes to the derivative of z in the direction of u, right? So I'm just using the z instead of f of x, y, as delta u goes to 0. Okay, so we're going to look at this in a little bit more detail. I've actually already shown this top view. Where am I? Moreover, if we move away from our point p equals x naught y naught, comma f of x naught y naught in the vector u direction scaled by h, we get delta x equals ha and delta y equals hb, which we saw from that top view. I'm going to do that one more time just to be clear. So the change in, as we're moving in this direction, my change in x, if we're moving in the u direction, is ab, but if we scale it down by h, then delta x equals ha and delta y equals hb. So our change in z is delta z equals f of x naught plus delta x, comma y naught plus delta y minus f of x naught y naught. Right, so here we're getting my z value. So we start at this initial z naught right here, and then as I move by delta x and delta y in the u direction, we get some new z sub 1, and when we do the difference of those, that gives me my change in z. Now delta x and delta y we know are HA and HB as discussed above, so we can define our directional derivative to be this definition, 11.1.1, the directional derivative of f at x naught y naught in the direction of the vector u equals a comma b is d sub vector u of f of x naught comma y naught equals the limit as h goes to 0 of, on top of a big fraction, f of x naught plus ha comma y naught plus hb minus f of x naught y naught all over h if this limit exists. So this is essentially going back to how we define derivatives initially in single variable calculus. We have f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h, right? It's the instantaneous change in the output over an instantaneous change in the input, where h is delta x in this case. So here it has to be a little bit more complicated for the 3 dimensions, but same concept. So while this is a working definition, it's not easy for use to use for quick computations. Instead, we use the following theorem, Theorem 11.1.1. If f is a differential function in x and y, then f has a directional derivative in the direction of any unit vector u equaling a comma b, and that directional derivative d sub u of f of x comma y equals f sub x of x comma y times a plus f sub y of x comma y times b. That is, we have the partial derivative of f with respect to x times a, where a is the x component of u, plus the partial derivative of f with respect to y times b, which is the y component of u. So in practice, this is really not too bad. Let's see here. Yeah, let's go ahead. I'm going to do the proof in a moment. Let's jump forward for a second before I do this proof, and let me do this example just so we can see how not bad this is to use. So I'm going to copy down our formula here, my directional derivative in the u direction of f of x comma y equals f sub x times a plus f sub y times b. These are implied to be f sub x of x comma y and f sub y of x comma y. So to do this, I want to find f sub x, my partial derivative of f with respect to x. So I'm going to get 1/2 times 1 minus x squared minus y squared to the negative 1/2 times, inside here the 1 and the minus y squared are considered constants, so minus 2x. And let's simplify this down. The 2's will cancel. We'll put this in the denominator. We're going to get a negative. Let's put that on top. Negative x over the square root of 1 minus x squared minus y squared. And f sub y is going to be the same thing, but with a y on top. And that's just by symmetry. This looks exactly the same in x and y. So we get f sub y equals negative y over the square root of 1 minus x squared minus y squared. So then, if we want to find the directional derivative, oh, we've got some extra work here, so let's read the problem. Example 11.1.1, given f of x comma y. Sorry, that was going to bug me. So given f of x comma y equals the square root of 1 minus x squared minus y squared, find the slope of the surface at the point 2/5, 2/5 in the direction of the unit vector u, which makes an angle of 2 pi over 3 with the positive x-axis. Okay, so let's find u real quick. So here's 2 pi over 3. So this vector has to be negative 1/2 comma root 3 over 2, because we're on our unit circle, right? It's a unit vector. So note this is exactly the example shown in figures 11.1.1 and 11.1.2. So the picture that we were looking at earlier is of this function, actually. So I want the directional derivative in the direction of negative 1/2 comma root 3 over 2 of f of 2/5 comma 2/5. Before I get to this specific, I'm actually going to go back and just say, what's the directional derivative in that direction for any xy? So this is going to be f sub x is negative x over the square root of 1 minus x squared minus y squared times a is negative 1/2. And we go plus f sub y is negative y over the square root of 1 minus x squared minus y squared, and that's times root 3 over 2. this can actually simplify nicely to, let's see, x minus root 3 times y all over 2 square root of 1 minus x squared minus y squared. Cool. So if I'm wanting to move in this direction, then I can look at any point x, y. So now we'll plug in our specific. Two-fifths, comma 2/5. So the directional derivative of f of 2/5, comma 2/5 in the direction -1/2, comma root 3 over 2 is going to be 2/5 minus root 3 times 2/5 over 2 square root of 1 minus 4/25 minus 4/25. When I plug in the 2/5 for x and y respectively, this equals, let's see, 1 is 25 minus 4 minus 8, so 17. And then this 2 and this 2 will cancel, so we'll get 5 on the bottom. I'm going to get 1 minus the square root of 3 over 5 square root of 17 over 25, which equals 1 minus the square root of 3 over the square root of 17, which is approximately negative 0.1775. So this is saying that if we move in the direction -1/2, comma root 3 over 2 in the u direction, the instantaneous, or at the point 2/5, comma 2/5, then the instantaneous change in z, the slope in that direction, is negative 0.1775. If I go and look back at our graph here, the slope of this line right here is that negative 0.1775 value. Okay, still before I have you do the proof, or before I do the proof, then let's have you try this exercise here, exercise 11.1.1. Find the directional derivative d sub vector u of f of x comma y if f of x comma y equals x cubed minus 3xy squared, and the vector u is in the direction of the plane x minus y equals 0. Note this gives two possible directions. What is the directional derivative d sub vector u of f of -2 comma -2? What does this represent? Go ahead and give this a shot. I will be back in a few moments to work through the solution with you. And we're back. So to do this, I find the partial derivative of f with respect to x, which equals 3x squared minus 3y squared. The partial derivative of f with respect to y equals negative 6x times y. Then the directional derivative in the direction of the vector u of f of x comma y equals parentheses 3x squared minus 3y squared times a minus 6xy times b, where u equals sum a comma b. Doing this generally, I can plug in the a and b later. I then think about what is my vector u. So if I'm looking at x minus y equals 0, this implies that y equals x. So if I'm looking down on the xy plane, then the y equals x line is going through the origin at a 45 degree, so u1 is pointing at the 45 in the first quadrant, and u2, I'm saying, is pointing at the 45 in the third quadrant. So that means that u1 equals the square root of 2 over 2, comma the square root of 2 over 2, and the vector u2 equals negative root 2, comma negative, missed it there. Sorry, let me say that again. The vector u2 equals negative root 2 over 2, comma negative root 2 over 2. So if I look at my u sub 1 vector, then the directional derivative d in the direction of root 2 over 2, comma root 2 over 2 of f of x comma y equals 3 root 2 over 2 parentheses x squared minus y squared minus 3 root 2 times xy. And here I've just plugged in the root 2 over 2 for a and b, and I did factor out that 3 also in that first term. And then if we plug in the specific point for negative 2, then I get the directional derivative in the direction of root 2 over 2, comma, root 2 over 2 of f of negative 2, comma, negative 2 equals negative 12 times the square root of 2. This is, since the x and y are the same, the x squared minus y squared just canceled out, and then negative 2 times negative 2 is 4, times negative 3 root 2 is negative 12. So the first line I had up here, this is my directional derivative of f of x comma y in the direction u1 for any point. So I could plug in any point x comma y and know what the slope is in that specific direction of u1. Then we're getting what the slope is at that specific point when I plug in the negative 2 comma negative 2. So now I look at the directional derivative in the direction of u2, negative root 2 over 2 comma negative root 2 over 2 of f of x comma y. This equals negative 3 root 2 over 2 times x squared minus y squared in parentheses plus 3 root 2 times xy. When I plug in the point negative 2 comma negative 2, we get that the directional derivative is positive 12 root 2. So the first slope, negative 12 root 2, this represents the slope of the tangent line to the surface, z equals f of x comma y, at the point negative 2 comma negative 2, in the direction of root 2 over 2 comma root 2 over 2. The slope, positive 12 root 2, this is the slope of the same tangent line but moving in the opposite direction, which is why it's the same thing but the opposite sign, right? So this should actually be expected because it's a single tangent line. It's just say, am I moving in the direction at the positive 45 in the first quadrant, or am I moving at the 45-degree angle in the third quadrant? But it's the same line, so we're just saying, you know, I can even pull up that picture again. So this is not the same problem. As we can see, we are on a spherical shape, which was from the previous example, not a cubic and parabolic that we're getting in this problem. So here we have an x cubed and then a 3xy squared. So these are both kind of cubic terms. This is definitely not that, but we can see if I have a tangent line, then the slope going this way is a negative change in z, and this is a positive change in z, but it's the same slope, just going in the opposite directions. All right. With that, let's go back and do the proof. So let's review what we're trying to prove here. So my theorem 11.1.1 says if f is a differentiable function in x and y, then f has a directional derivative in the direction of any unit vector u equals a comma b, and that directional derivative equals the partial derivative of f with respect to x times a plus the partial derivative of y of f with respect to y times b. So we've been using this formula on the last two problems. We just want to prove that this formula does in fact give us my change in z in that direction like we want it to. So we're going to start by letting, it's going to be a little bit weird, but let's let g of h equal f of x of h comma y of h. So remember, we had initially f of x comma y equals z. And we're now rewriting this so that it's a function of the single variable h. And we're going to note that we're letting x equal x naught plus ha. So essentially if we'd started at some x naught and we're moving over by some delta x, then that's giving me my new x. And y equals y naught plus hb, same idea. hb is a delta y. And we're starting at some y naught, so our new y value is given by this. So we're able to define this new function g as the outputs of f as we change h, as we get farther and farther from our specific point. So we've got our specific point here. As we move from this point in some direction, so we're going out here in the direction of h times u, then what are the z values of my function going to be as we move in this direction, right? So we are still getting the z values of the function, but we're now only doing it as we move in this direction as we have defined my function g. So the derivative of g prime, we're going to get by the chain rule. So g prime of h. So we're taking this with, now we're thinking of this as a function of h, right? As we move, as h changes, we're moving along our surface in the u direction. So as we move in the u direction, my derivative equals, by the chain rule, the partial derivative of f with respect to x times dx dh plus the partial derivative of f with respect to y times dy dh. Right? That's from chain rule that we did in previous sections on a function of two variables where each variable is defined by a single variable. This is exactly f sub x of x comma y times a plus f sub y of x comma y times b, since partial of f with respect to x is f sub x and partial of f with respect to y is f sub y. Dx dh, when we're looking here, x naught is a constant, a is a constant, h is a variable. So this derivative is just a, and the derivative of y with respect to h is just b. So we're able to plug in those respectively. Now, from the definitions of x of h and y of h, that if h equals 0, then x equals x naught and y equals y naught. Therefore, by the above equation, we have g prime of 0. So if I plug 0 in for h, we get f sub x of x naught y naught times a plus f sub y of x naught comma y naught times b. So, right, if I plug in 0 here, then 0 for h gives me y naught for y and x naught for x. So we're just plugging that in for x and y right there. Okay, now we're going to find the derivative for g prime of 0 in a completely different way. So we're going to say, okay, g of h, if we are thinking of this as just a single variable function, which it really is. Once we've plugged in x naught plus ha for x and y naught plus hb for y, we could just think of this as a function in h, not a multivariable function in any way. So we can use single variable calculus to take the derivative and know that g prime of 0 equals the limit as h goes to 0 of g of h minus g of 0 all over h. That's just my basic derivative definition. Well, g of h is going to equal f of x naught plus ha comma y naught plus hb minus g of 0, which is f of x naught comma y naught. And then this is all over h. But this is exactly the definition of our directional derivative. So we go back up here, definition 11.1.1, my directional derivative we had defined to be exactly that limit. So we can equate these things now. We've now found that g prime of 0 equals f sub x of x naught comma y naught times a plus f sub y of x naught comma y naught times b, and it also equals my directional derivative. So my directional derivative in the direction of u of f of x naught comma y naught equals f sub x of x naught comma y naught times a plus f sub y of x naught comma y naught times b. So we can then say, okay, this was if we'd started at a specific x naught y naught, but we could start at any x naught y naught that we want, and doing that we would get our result that we have up here in the theorem, that the directional derivative d sub vector u of f of x comma y equals f sub x of x comma y times a plus f sub y of x comma y times b. That's it. That's our proof. So this should work, and we've used it now. So let's go ahead and move on down and talk now about the gradient vector. So we're going to talk kind of about the exact same things, but just in a slightly different way. All right, so section 11.2, the gradient vector. If we look back at our directional derivative formula, d of vector u of f of x comma y equals the partial derivative of f times with respect to x times a plus the partial derivative of y of f with respect to y times b. That we could actually factor this as a dot product. So we could write that the directional derivative in the direction of u of f of x comma y equals the vector f sub x of x comma y comma f sub y of x comma y dotted with the vector a comma b. So this vector on the left, we call this right here our gradient vector, and we notate it. The gradient is an upside down triangle of f of x comma y. And let's note that our definition 11.2.1, given a function f of x comma y, which is differentiable in x and y, then the gradient vector is defined to be this upside down triangle f of x comma y equals the vector partial derivative of f with respect to x, comma, partial derivative of f with respect to y, that this is a vector-valued function. So this gradient vector is not a constant vector, it is a vector-valued function in two variables. So we're going to kind of talk about the same idea of directional derivative, but in terms of this gradient vector. Exercise 11.2.1. And so this is for you. It's an exercise. Given f of x comma y equals xy cubed plus 2x squared y, find the gradient vector. And then find the directional derivative to f at the point 2 comma 1 in the direction of the vector v equals 2 comma 3. So, and use the gradient vector in your calculation instead of the general formula that we were using before. All right, so go ahead and give this a shot. Now you try. And I will work through the solution with you in just a few moments. And we're back. So working through this, I'm going to start by finding the gradient vector function. So the gradient of f of x comma y equals the vector y cubed plus 4xy comma 3xy squared plus 2x squared. So my directional derivative in the direction of v of f of x comma y equals the gradient of f dotted with the vector v. This equals the vector y cubed plus 4xy comma 3xy squared plus 2x squared dotted with 2 comma 3. Oh, I totally made a mistake. Let's fix this up here. We need a unit vector, not the original vector, so we need to find u. This equals 2 comma 3 over the square root of 4 plus 9 equals this vector 2 root 13 over 13 comma 3 root 13 over 13. So let's make a couple of quick adjustments here. Switch to blue to note my edits. So this now is going to become 2 root 13 over 13 comma 3 root 13 over 13. And now all of this is going to change. I'm probably going to need more room here, but let's see if I can't squeeze it on. So this is 2, 8. And 3 times 3 is 9. And 2 times 3 is 6. Okay. And then if I plug in a 2 and a 1, all of this is going to change. So we are going to get negative 2 root 13 over 13. 2 for x, negative for y is negative 16 root 13 over 13 plus 2 for x. 1 for y squared is plus 18. It's going to be the same thing I had before, but with the scalar. Plus 24 root 13 over 13 equals, okay, these all cancel and I get 24 square root of 13 over 13. Okay. I'm all of a sudden not sure what I need to explain here now that we walked back through that. So I dotted this. My directional derivative is going to equal the vector y cubed plus 4xy comma 3xy squared plus 2x squared dotted with the unit vector now 2 root 13 over 13 comma 3 root 13 over 13. When we take that dot product, we get that this equals 2 root 13 over 13 times y cubed plus 8 root 13 over 13 times xy plus 9 root 13 over 13 times xy squared plus 6 root 13 over 13 times x squared. When we plug in the specific point, so this function right now that we have, this is going to give me the slope in the direction of 2 comma 3 at any point on the surface. So when we plug in the point 2 comma negative 1, this equals 24 root 13 over 13. So that's the slope in the direction of v at the point 2 comma negative 1. So same kind of thing that we were doing before, but using this new gradient vector. So now we can talk about all of this in functions of 3 variables. Section 11.3, functions in 3 variables. For a function w equals f of x comma y comma z in 3 variables, we can define the directional derivative, capital D sub vector u of f of x comma y comma z in the direction of the vector u equals a comma b comma c, similarly to how we did when working in 2 variables, simply by noting that this new directional derivative tells us that the rate that we move between the level surfaces of f, the rate of change, the rate that w changes from a given point in a given direction in 3 dimensions. Everything we've done simply scales up. So the idea for a function in 3 variables, remember, I kind of want to pull up an old graphic that I don't have prepped right here. I'm going to pause the video 1 second. Okay, so that wasn't really a second for you, but it was for me. I've got this here, which is showing these level surfaces for a function x squared minus y squared minus z squared equals w. So here w equals 1, and we get an orange surface, or a red surface that is here. And then this is when w is 0. We get a different level surface. Purple is when w equals negative 1, and blue is when w equals 5. So blue is actually the innermost here. So we see if we move from, come on, let's get rid of that. So if we're at negative 1, I wish these wouldn't disappear. So negative 1, 0, 1, 5. So as w, as we are trying to get our outputs to go from negative 1 to 5, we see that the level surfaces are moving from the points on this plane to the points on the red, not plane, on the blue surface to the red surface to the cone, the green surface, to the purple surface. I totally just said that backwards. Of course I did. Okay, say this one more time. So purple is negative, green is 0, red is positive 1, blue is positive 5. So if we want an output of negative 1, we're on this purple surface, and then as we move from points on the purple surface towards points on the green cone, then we're going to go from outputs of negative 1 to outputs of 0. As we move from the surface on the green cone to the surface on the red hyperpoloid of 2 sheets, as we move from there, then our outputs are going from 0 to 1. As we move from this hyperboloid of 2 sheets to the blue hyperboloid of 2 sheets, we're going from w outputs of 1 to w outputs of 5. So if we think about the directional derivative, we're really thinking about moving in a 3-dimensional direction, say, and we want to say how quickly, if I'm moving in some 3-dimensional direction, so we could be moving along this surface, in which case the outputs are not changing at all. But if I'm moving at a right angle to this surface, then I'm moving towards greatest change in the outputs. So I hope that kind of helps clear up what we're talking about as I look at this here. So when we're in practice and we're trying to find the gradient vectors and the rates of change of w, how quickly are the outputs changing as we move in a certain 3-dimensional direction, we can do all of this in the same way that we were just doing it, but scaled up. So we define the directional derivative of f at a specific 3-dimensional point, x naught, y naught, z naught, in a 3-dimensional unit vector u equals a comma b comma c. This is going to be d sub vector u of f of x naught, y naught equals the limit as h goes to 0 of f of x naught plus ha, comma, y naught plus hb plus z naught plus hc minus f of x naught, y naught, z naught all over h, if this limit exists. So now this ha is my delta x just as it was before. The hb is my delta y, and the hc is my delta z. So as x, y, and z all change in the direction of a, b, c, then my outputs, my w outputs are changing, and so this difference on top is my change in w, and h is essentially my change in u. So this is essentially change in w over change in u, and we're letting this go, the change in u go to 0, so this goes to we can't say dw du because of we're not in a one-dimensional situation, so we use this notation here. Could write it like as a w, yeah? So definition 11.3.2, given a function f of x comma y, which is differentiable in x, y, and z. Of course, I've got a typo here. So given a function f of x comma y comma z, I went through this to try and make sure, but I always miss a little something. That's all right. I'll get that fixed. So given a function f of x comma y comma z, which is differentiable in x, y, and z, then the gradient vector is defined to be the gradient of f of x comma y comma z equals the partial derivative of f with respect to x, comma, partial derivative of f with respect to y, comma, partial derivative of f with respect to z. Again, notice that this is a vector-valued function whose components are giving the derivative of f in the x direction, the derivative of f in the y direction, and the derivative of f in the z direction, respectively. So, yeah, defined exactly the same as we did in 2 dimensions, just scaled up. Now we have our theorem 11.3.1. If f is a differentiable function in x, y, and z, then f has a directional derivative in the direction of any unit vector u equals a comma b comma c, and the directional derivative d sub vector u of f of x comma y comma z equals partial derivative of f with respect to x times a plus partial derivative of f with respect to y times b plus partial derivative of f with respect to z times c, which equals the gradient of f dotted with the vector u, just as we had before in 2 dimensions. So I'll do this example here. Example 11.3.1. If f of x comma y comma z equals x sine of yz, find the gradient of f and use it to find the directional derivative at 1, 3, 0 in the direction of the vector 1, 2, -1. You do not want to forget to make this a unit vector again, so I'm going to do that right now before I forget. So we have 1, 2, -1 divided by the square root of 1 plus 4 plus 1 equals the vector, this is square root of 6 over 6, comma, square root of 6 over 3, comma, negative square root of 6 over 6. And so we've got the gradient vector of f this is going to equal the vector. When I take the derivative with respect to x, then sine of yz is thought of as a constant, so we just get that. When I take the partial derivative of this with respect to y, x is now a constant. I have to take the derivative of sine, so I get x. I'm going to have a z here. I'll plug that in, I'll explain in a second. Cosine of yz, we had to use chain rule, so the derivative of yz is just z when I'm taking the derivative with respect to y. Comma, I'm going to get the same thing here because we've got symmetry inside the sine function, so I'm going to get xy cosine of yz. Alright, so here's my gradient vector function. We can go ahead and actually do this at this point right now. So the gradient of f at 1, 3, 0 is not a pretty number. Sine of 0 is 0. That's nice because of my z value. Oh, that's sweet. That's going to make all of these sines and cosines much nicer. So x is 1, z is 0, so this is 0 again. and x is 1, y is 3, so we've got 3 out here. Cosine of 0 is 1, so this is a 3. So the gradient vector at the point 1, 3, 0, this is saying that my change in x at this point is, if we were moving in the x direction, my change in w would be 0. If we were moving in the y direction only, then the change in w would be 0. If we were moving in the z direction only, the change in w would be 3. So we're seeing that we're only seeing a change in w if we move in the z direction right here. Now we want the directional derivative in the direction of u at this point f of 1, 3, 0. So this is going to be the gradient of f dotted with u, so the gradient of f is 0, 0, 3 at this point, dotted with the vector u, which is root 6 over 6, comma, root 6 over 3, comma, negative root 6 over 6. And when we dot these together, the first couple of components are going to cancel to 0, and we get minus root 6 over 2. So this is saying that the change in w, the change in my outputs of this three-dimensional function, is negative root 6 over 2 when we move in the direction 1, 2, negative 1. All right. Now we get to the topic, section 11.4, maximizing the directional derivative. So this is saying we want to know if we have a function in 2 or 3 variables and we want to be able to find what direction, if we're at a specific point, we want to find which direction is giving me the steepest increase in my outputs, right? The quickest increase in my outputs. What direction is that? So let's take a look at how we can find that. Suppose we want to know the direction in which our outputs are increasing most rapidly. In 2 dimensions, this would be the direction in which our surface is most steeply uphill, and in 3 dimensions, this would be the direction in which we are moving between level surfaces the most quickly. It turns out that the answer is quite simple. So Theorem 11.4.1, given a differentiable function z equals f of x, y, and a point x0, y naught, then the gradient of f of x0, y naught is the direction in which z is increasing most rapidly from x0, y naught, and the magnitude of the gradient of f at x0, y naught is the maximum rate of change of z from x0, y naught. So when we say from x0, y naught, I'm just saying as we move away from this point. So so say you're on a hill, right, and you're walking along some path, and so you're walking along here and you want to say, okay, well, it's flat right at this point, so there's no change in any direction. But if I'm at this point, then we see that, so say it's kind of flat in this direction, then the greatest uphill is actually back here. If we were right here, we could see that the greatest, so if it's kind of flattish here, the greatest direction of uphill is in this direction. So if I'm moving from a specific point, x0, y naught, that's going to happen every time I try and stay on a point. So if we're at some x0, y naught, and I try and move away from it, which direction is the direction of greatest uphill, greatest change in z, this direction here? So similarly, given a differentiable function w equals f of x, y, z, and a point x0, y naught, z naught, then the gradient of f of x0, y naught, z naught is the direction in which w is changing or increasing the most rapidly from that point x0, y naught, z naught, and the magnitude of the gradient function at that point x0, y naught, z naught is the maximum rate of change of w from our point x0, y naught, z naught. Okay, so in other words, if we want to find the direction of steepest ascent given a function in 2 variables from a certain point, all we need to do is plug that point into the gradient vector, and voila, we have our direction of steepest ascent. And to find the slope in that direction, to find out what that steepest ascent is, all we need to do is take the magnitude of that direction. So to prove this, very simple, the definition of the dot product. So if I have my directional derivative d sub u of f, this equals the gradient of f dotted with u. This equals the magnitude of the gradient times the magnitude of u times the cosine of theta. Now the magnitude of u is 1, so this equals the magnitude of the gradient of f times the cosine of theta. So this directional derivative is going to be maximized when cosine of theta is 1. So its greatest, the greatest directional derivative for some point is going to just be the magnitude of the gradient of f. So this occurs when the gradient, so this cosine of theta equaling 1 is how we're going to maximize this. So the maximum is the absolute value of the gradient, or the magnitude of the gradient, if you will. And to get the cosine of theta to equal 1, then theta, which is the angle between my u vector and my gradient vector, that's going to happen when theta is 0. So the angle between my u vector and my gradient vector is 0. In other words, when they're pointing the same direction. So if the direction of u is in the direction of the gradient vector, then we have the direction of maximum increase. And this proof was for for really any dimensionality that we wanted to. We didn't use x, y, or z or anything in this. So this is proving it for both of those. So really nice, simple thing to have. And so go ahead and do this as an exercise. Given f of x comma y equals 4x to the fourth plus 4xy plus 3y squared, find the direction of maximal increase from -1 or comma -1 and the value of the slope in that direction. So this is a now you try. Go ahead and hash this out on your own, and I will work through it with you in just a few moments. And we're back. So to find the direction of maximal increase, we just find the gradient vector. So the gradient of f of x comma y equals 16x cubed plus 4y comma 4x plus 6y. We want to find the gradient at our specific point, so I plug in -1, -1, and we get that our gradient vector equals -20 comma -10. So this is the direction of max increase. This is the direction that we are going to be going uphill the most steeply if we're sitting on the point -1, -1 and trying to move away from that point. So the magnitude of this gradient, the magnitude of the gradient of f of -1 comma -1, this equals a square root of 500 equals 10 root 5, which is approximately 22.4. This is the max slope moving from the point -1, -1. Okay, actually, I'm going to go ahead and pull up a graph of this so we can see it. Okay, so I have a top view here, so we can't really see the shape of the graph yet, but I just want to note that -1, -1 is right at this grid point. And I've got the z-axis scaled up quite a bit. If this is a normal 1-to-1, oops. And this is a really tall, skinny, I mean, we've got 4th degree, 2nd degree, and 2nd degree all being added together. So this is increasing quite rapidly. So I kind of zoomed it out here. And so this right here is my -1, -1 point. Keep track, it's right here. And we see that in the direction -20, -10, so this is the same thing as -2 in the x direction, -1 in the y direction. So if we're moving this way, then we're getting the steepest descent. And sure enough, it looks like we're quite steep in this direction, moving out in this direction. We are the steepest. And the slope at this point is, as we move in that direction, what did we say it was? Boom. 22.4. So we can see that this is a height of 20 right there. So if we move out 1 unit in this direction, we have moved up about 22.4. So that's what all of this is doing. Okay, cool. Glad we did that. So one other thing that we want to say about the direction of maximum increase is that it's always at a right angle to the level curves or level surfaces of our function. So if we have a function z equals f of x comma y, if we set z equal to some constant, we get our level curves, right? Traveling along this level curve means that we have no change in z, so it becomes intuitive that the direction of greatest increase in z is when we travel orthogonal to these level curves. Let's take a look again at that graph. So we don't see level curves here, but say we wanted to stay right at this same height. So a level curve might be somewhere right in here, kind of hard to tell, but if we stayed right on a level curve, the change in z is 0, and then if we were at a right angle to that level curve, that's when we're going uphill most steeply. So think about if you're walking along a trail on a hill, hiking, and you are on the path, so the path is nice and level, you're not changing height barely at all. Say you're actually going on a flat path that's just traversing the side of the hill, and if you turn 90 degrees, that's where you're going to go straight uphill at the most steep angle. And if you move just slightly off the path, you're going to be going uphill a little bit, but not very much, right? The closer to 90 degrees, the more straight uphill you're going. If you're going opposite of just traversing the hill at a constant elevation. So we can actually use this now in a three-dimensional argument in our next section, 11.5, tangent planes to level surfaces. So suppose we have level surfaces given by f of x comma y comma z equals k for some real number k. So we have a three-dimensional function, a function in 3 dimensions, I should say, that's outputting some w value, and we set the w equal to some constant, so we get a level surface. And we want to know, well, okay, let me just read this. As we noted at the end of the previous page, the gradient vector to a level surface will be orthogonal to the surface. Well, what I was saying on the previous page was that the gradient vector to a level curve will be orthogonal to the curve, right? I'm saying if we are, the gradient vector is going to give me the direction of maximal increase, so that has to be at 90 degrees to the level curve where we're not changing elevation at all. So similarly in 3 dimensions, if we have a gradient vector, it's going to be, the level surface is where we're not changing output values at all, right? The output's staying the same. So my derivative, as long as I'm staying on that level surface, is 0. So if I want to say how am I going from an output of k to an output of bigger than k as quickly as possible, then we want to move from this level surface at a right angle. Let's take a look at this graph that we had again, where we have these level surfaces that are hyperboloids in one sheet, a cone, and hyperboloids in 2 sheets. So remember, everything on this purple surface is where my w value is -1. Right? So if I want to get from a w value of -1 to a w value of 0 on the cone as quickly as possible, I want to move at a right angle from the purple surface towards the green cone. I don't want to move at some angle that's slowly moving towards the green cone. I want to move straight towards that green cone, which is going to be at an orthogonal vector to the purple surface. That's what we're saying here. And we want to do a little proof of this. So I think conceptually this kind of makes sense, and my proof is going to be a little bit of a roundabout, but let's see if we can't follow it here. So let c equal the vector r of t equal x of t comma y of t comma z of t be a curve on the surface given by f of x comma y comma z equals k. So we've got some surface, and like say we've got my hyperboloid in one sheet, and we draw on this a curve. So this curve is some curve on the surface here, and since the curve is on the surface, if I plug in x of t, y of t, z of t into the function, we should still get k because every point on the curve is on the surface, so we should still output the same thing. So we can take the derivative with respect to t of our function when we have x of t, y of t, z of t plugged in, and we take the partial derivative of both sides, right? So the partial derivative of k is 0. The partial derivative of f of x of t, y of t, z of t, we're going to use the chain rule and get that this is the partial of f with respect to x times dx dt plus partial of f with respect to y times dy dt plus partial of f with respect to z times dz dt, and this equals 0 since the partial of k with respect to t is 0 because my k value is not changing. We can factor out this chain rule expression that we have here as the partial of f with respect to x, comma partial of y with respect to, or partial of f with respect to y, comma partial of f with respect to z as a vector, dotted with the vector x prime of t, y prime of t, z prime of t, and this equals 0. So this then can simplify down to the gradient of f dotted with r, the vector r prime of t equals 0. Now, since the vector r of t is an arbitrary curve on the surface, then r prime of t is a vector tangent to the surface. So if I take any point here, I'm on this curve, then the tangent here is going to be a tangent vector on the surface in any direction. And because this curve is any curve on this surface, so I've generalized every curve that goes through this point on this surface. So this vector r prime of t dotted with our gradient vector has to equal 0, but since r prime of t is any vector, the only way that we can guarantee that we're going to dot product with this gradient to be 0 is when the gradient vector is orthogonal to every tangent on the surface. So the only way for a gradient vector to be orthogonal to every tangent vector from a given point on the surface is if it is orthogonal to every one of those which is at a 90 degrees to the surface itself. Okay, so that's our proof. And hopefully conceptually, more than anything, that kind of rings true with you. So we're almost done here for this lesson. Definition 11.5.1 is given a level surface f of x, y, z equals k, and a point P on this surface. The normal line to the surface through this point is the line through the point that is orthogonal to the surface. So here, I guess I should really be bolding this. This is what we're defining the normal line right here. So I'm defining a normal line through a point on a surface to be the line that goes through the point at a orthogonal, in an orthogonal direction to the surface. So in example 11.5.1, we want to find the tangent plane and the normal line to the surface. X squared plus 1/4 y squared plus 1/9 z squared equals 3 at the point 1, -2, -3. So if we say, so what we want to do is we want to take advantage of this whole idea that we're talking about here, that the gradient vector is going to give us something that is orthogonal to the surface. So instead of thinking of this as a equation in x, y, and z, I want to redefine it as a function f of x, y, z equals x squared plus 1/4 y squared plus 1/9 z squared. And we're saying f of x, y, z equals 3. So this is giving me the level surface, which is this ellipsoid. So if I get my gradient of f, this is going to be, well, this is nice because there's no x times y or times z anywhere in here. So my partial in the x direction is 2x, my partial in the y direction is 1/2 y, and my partial in the z direction is 2/9 z. And if I plug in any point for this gradient, into this gradient, this is going to give me a vector that is orthogonal to the surface in question. So the gradient of f at 1, -2, -3, this equals 2, -1, -2/3. So this is a direction that is orthogonal to the ellipsoid at the point in question. So this is a normal vector to my tangent plane. I'm going to actually scale this up. I'm going to let my normal vector, because it doesn't need to be a unit vector to find an equation of a plane or to find the equation of a line, which we're going to do here in just a second. I'm going to let this be 6, comma, -3, comma, -2, just so I don't have to deal with any fractions here. So then the equation of my plane, tangent plane, let's call this the linearization, at the point 1, -2, comma, -3, that's my tangent plane. This is a function in x, y, and z. This equals we're going to get this in a second. Let me back up. I am jumping the gun just a hair here. Where's my... I want to use my standard formula, so 6x minus 3y minus 2z equals d. The point in question is 1, -2, -3, so I can plug that in and get 6 plus 6 plus 6 equals d. So the plane, the tangent plane, is given by 6x minus 3y minus 2z equals 18. I can, let's not worry about writing it in the linearized form, but we could solve for z and write it in that form if we wanted to. The equation of the normal line is a vector function in 3 dimensions, so let's call that r, and this is of t. This equals the point that we start at, 1, -2, comma, -3, plus t times the direction of the normal vector. So 6, -3, -2. This is the equation of the normal line. All right, and that's it. That is our lesson for the day. Thank you so much for watching, listening, and I will talk to you all in the next lesson. Have a great day.